Thank you. Okay. All right. Everyone, Dr. Hrushikesh Mhaskar is emeritus at Claremont College. It's an Institute of Mathematics in California, in Fairmont, California. Actually, Dr. Mhaskar and I met, I don't care to say exactly when, but many years ago, let's say decades ago. And he's done tremendous work in I think when we met, we were both working on wavelets or something to that effect. But he's done a lot of work in approximation theory and harmonic analysis and many other things, and neural networks for that matter as well. And today he's going to be talking to us about orthogonal polynomials, actually, which are I think emerging as being of cardinal importance in machine learning, and I am certainly interested because there is one aspect that's of great interest to me. In fact, Dr. Mhaskar and myself are actually working on collaborating on some work along that line. And without further ado, it's a pleasure to have you. Thank you for accepting to give a talk, and the floor is yours. And you should be able to share your slides. I think I already allowed it. Yeah.
Can everybody see my slides and can everybody hear me properly?
Yes.
Great. So I'm not going to talk so much about orthogonal polynomials and their theory, but more about some questions in machine learning and signal separation and such, which I'm working on right now. And so this is the formal title of my talk. Then what I'm going to do is there are three main topics I want to talk about. One is the localized polynomial kernels, including signal separation applications. I'm quite excited to be somewhat nervous also to be talking in front of Professor Krim because he's such a great expert on signal separation problems, but I do have some questions about it for him afterwards. And then I want to explain two of my recent ideas about machine learning and how one could modify it hopefully in a better way. So here is the basic problem of machine learning. We have given such a random data and we want to find some kind of functional relationship between them. So that's like a black box. But given this data, we want to build some model like a neural network or something like that. And hopefully it will approximate the actual functional relationship. So here is how people normally do this in very general terms from textbooks. We assume that this F belongs to some nice space like a reproducing kernel Hilbert space or something. And then we want to minimize something called the empirical risk. But in order to set up this problem, we have to figure out what should be the architecture of the machine. So the role of approximation theory is classically to determine what is the distance between this unknown function f from whatever class you are contemplating. But then this doesn't play any role in the actual practice of machine learning. It just stays there. What they're interested in theoretically is the minimizer of what is called the generalization error. But what they can actually compute is just the minimizer of the empirical risk. And there is no connection between these three minimizers in general. But nevertheless, that's the state of the art. And I was always wondering, as this symbol shows you, from ever since I was introduced to this topic, why can't we use the approximation theory techniques directly? There are many papers dating back to 1937 and on, which deal with exactly this problem. You are given some data and you want to approximate the function. How can you do this? So then I started collecting what is wrong with what is the current paradigm. And then these are some of the things which I noticed in recent years. One is a paper by Lulu and Karniadakis and some other people. They observed that when you try to train a deep ReLU network and start with a random selection of weights, it could become dead on arrival. So it doesn't train properly at all. It's very sensitive to the initialization of the weights. And then a couple of years ago, I published two papers where I observed that this whole paradigm doesn't really work. So if the objective of finding this degree of approximation to get some insight into this V sub n, that is not going to work, because I found out an example where for the same class of functions, and you want to approximate by shallow ReLU networks, then for the same class of functions, you get drastically different results on what kind of accuracy to expect in this approximation, depending upon whether you want to do it data-based like this, or whether you are just interested in approximation of functions. So that's completely useless. And then the other thing which will be one of the main topics of today's talk is to do like this, that everybody tries to train directly from the data. So necessarily the loss functional is a globally defined quantity like the L2 naught. But that hides local effects. So if the function is bad at small number of points, it will affect the error everywhere. So my goal here is to do this directly. I'm not against optimization, but I would like to avoid a direct optimization to do this learning. So I want to find a direct method so that you give me the data and I give you the approximation, and then I can find out what is going to be the approximation error. So you don't find V sub n depending upon the approximation error. You first decide V sub n, find out this approximation, and then figure out what kind of error to expect. Okay, I have spent many years in approximation theory, but so I should emphasize here that I'm not looking for a better degree of approximation. There are already theorems which other people have done in this direction. And I'm not claiming that the method which I'm going to say is going to be better than everything else. Partly because I don't want to make enemies, and partly because I don't believe it myself. And the third thing which I'm stuck about is the problem of how to select the right features. So people claim that deep networks nowadays can do this automatically. But everything theoretical I have seen in that regard is kind of tautological. It must be doing the right thing because it works, but who knows whether it will work or not. So that's not, I don't know yet how to do that. The other point I want to make is about classification. So most of the problems in machine learning are about classification, not so much about regression. But the classification, if you look at any textbooks, is reduced to approximation of this function. So you look at the characteristic function of class I, and then look which class gives you the maximum of the approximation to this characteristic function. That's how the support vector machines and deep networks and everybody works. My question is this the right approach? Because from an approximation theory point of view, to get a good approximation, we need a smooth function. And in theory, there is a smooth function, but if the class boundaries are touching each other, or they are very close or very irregular, then it doesn't become constructive anymore. So can we do something else? And my proposal is that we should treat classification as a super resolution problem. So as Professor Klim mentioned, I have worked for many years, and he was one of the leading people whose work inspired me also, that we are given the Fourier transform of a linear combination of Dirac deltas. And we sample this at certain number of points, and then we want to figure out all the omega k's and all the a sub k's, and if possible also the number of signals here. So my thinking was, suppose we have two classes, and of course the classes should be disjoint even if they can touch each other. And let's say that the first class arises from probability distribution mu1, the other from mu2. And we are observing a random sample taken from a convex combination. So instead of finding out these omega k's, we want to find out the supports of the mu1 and mu2. So by the way, can you see my cursor also?
Yes.
So that's the other theme which I'm trying to develop. And one advantage here is that if I can manage to do this, then I just have to take one sample from U1 and one sample from here, and then we are done with 100% classification, just with as little information as possible. Okay. So the main thing behind all this theory is the notion of localized kernels. So what happened was in 1991, Charles Tree was writing his famous book on wavelets, and he tried to teach me what wavelets are. And my immediate question was, what is wrong with Fourier coefficients? So one thing was, if you are using wavelets, then you can figure out what is going wrong here. If you are using Fourier series, then two bad points are affecting the error everywhere. So you need local approximation. Okay, but can we improve this? And the conclusion was, yes, we can. As you see, if you use the method which I'm going to introduce, with exactly the same number of points, 128 points, you can reduce the error significantly, logarithmically, like 10 to the minus 3.5 instead of 10 to the minus 2. So I think that's a substantial improvement. The data is the same, but we just use a different method. So the question is, can we get a wavelet-like frame expansion based on Fourier coefficients? Okay, the essential ingredients are like this. This is the class of all trigonometric polynomials of order n. This is the so-called degree of approximation. And in this whole lecture, I will be only interested in the sup norm. Although the theory will go through for every other norm also. By the way, wavelet analysis does not work for sup norm approximation. It only works for L2, and in some cases for LP strictly between 1 and infinity. This theory is going to work for sup norm especially, but also every other norm, including the L1 norm. So here is the approximation theory way of defining smoothness. Open some old book on approximation theory like Lorentz or Timan or Natanson even, and they characterize functions like this in terms of number of derivatives and Hölder condition of this nature. If gamma is an integer, then we need something more elaborate, which is not possible if you're not in the circle. Okay, so the idea of local smoothness is so that you look at the neighborhood of the point, so that for every C infinity function, if I multiply this f by that C infinity function, then the resulting function will be in the smoothness class gamma. So the idea is that this function is zero outside. You are focusing entirely on a neighborhood of the point x0. A typical example which motivated my work was these two examples. The characterization I gave you tells you that they are both in the smoothness class half, but this function is analytic away from all these points. And this is the famous nowhere differentiable function of Weierstrass. So how can we distinguish between the two? You don't want to get this as your signal. You would prefer to get this signal. Okay, so my solution was to develop some localized kernels based on Fourier series. So I start with a low pass filter, but it's critical that it should be 1 in a neighborhood of 0. There are many constructions like this, but this is what makes things tick. And then I define such a kernel. It has such a localization formula. If you draw the graph globally, then it looks like a very sharp Dirac delta. If you go away, then you see that it is decreasing exponentially fast. as the degree increases. So based on this, I can construct my reconstruction operator. And the nice property of that operator is that this is a near best approximation. Of course, it is not the best approximation, but near best in this sense. Okay. Then to construct frames, I need a analysis operator, which is just the difference between these two operators. And then in order to complete the analogy with wavelets, I need to introduce another kernel, which looks almost like this, but slightly different. It covers the whole frequency range for tau j's. And so then you can express this tau 2 to the j. Sorry, I should have written tau to the j in terms of this integral. When you discretize this integral, then you get a complete wavelet-like expansion. So here you have an expansion in terms of the tau j's, which is convergent uniformly. And you can write it like a wavelet expansion where the vjk's denote the time localization and j denotes the frequency localization. You have the frame property and you have a complete characterization of the smoothness class just in terms of finitely many of these coefficients. Okay, so that's classical kind of theory. The term wavelet-like expansion corresponds to the fact that you can characterize smoothness. But you can also characterize local smoothness. That was the most interesting thing from my point of view. The CJKs are defined in terms of Fourier coefficients. But if you are interested in figuring out what is the local smoothness, then you just have to look at those coefficients whose time localization is in a small neighborhood of that x0. And then the behavior of those coefficients completely characterizes the smoothness. So here is how tau 32 would look like. In my notation, tau 5 would look like for this function. You can see that this is there is a sparsity here in terms of, so if you threshold this, then you won't get too much error. We can solve the machine learning problem also in this way. You use the same kernel, take the expression for sigma sub n and discretize it using Monte Carlo. And then one can prove that in the supremum norm, it gives you the optimal rate of approximation. Of course, in every other norm also. So then in the trigonometric case, I have demonstrated that we can develop a substitute for wavelet analysis based on Fourier coefficients. We don't need all these elaborate wavelet constructions and what is called the sin of wavelet analysis. And we can do all the local approximation stuff. But our analysis is valid in uniform norm and based on Fourier coefficients, also scattered data. We can detect singularities of arbitrarily high order derivatives, unlike classical Daubécius wavelets, which have only finitely many vanishing moments, so they cannot detect discontinuities and derivatives of order higher than 3. And then I have solved the problem of machine learning directly without any optimization, without any empirical risk minimizer, generalization error, whatever. So here are some applications of these localized kernels, and I wanted to, as I said, I'm feeling kind of nervous presenting this, but I hope he will give me his comments after the lecture. So here is the problem of signal separation. We are given a data of this form. So there are m snapshots of some complex signal. It may or may not bear some signal, but basically this matrix is of this form. And then there is a famous survey by Professor Prim where he argues that the beam forming techniques are not adequate, and then he proposes subspace methods where they estimate the signal space and noise space via some singular value decomposition. When I looked at this, I was very surprised that it seemed as if people are focusing just on the noise and they are not paying attention to the spatial structure of the matrix. I might be wrong there, but that was my impression. So instead of that, I'm proposing that we just look at the prominent peaks of this expression. Instead of the Fourier coefficients, now I have YML, and this is the same filter which I had introduced earlier. So this is like the sigma operator for such a signal. But because there is noise, then we need some snapshots. So I took some random example here where I had three signals which are like this. And I want to note that these two signals are very close to each other. The imaginary parts of these are all, these are like the coefficients. They are all mean zero normal variables with such large standard deviations. The noise was also very large with standard deviation 1000. And then I used the MATLAB command to figure out what was the SNR in a few cases. It was ranging between -16 to -19 dB. And here is how the signal looks like. Using this method, we can detect all three peaks very accurately with only 512 values of n and 16 snapshots. Okay, the noise is suppressed. And we can do this with sub-Gaussian noise. We don't need normal noise. Then we tried it for multivariate signal, and I hope Professor Krim will tell me how it comes up in engineering. But anyway, from a mathematical point of view, this is the problem. Instead of having one-dimensional signal, now we have a high-dimensional signal. And we want to find out the number k here and AKs and the WKs. But of course, the most important is what is capital K and what are the WKs. Okay. So the question is, how many samples do I need to get this accuracy? We are doing a q-dimensional inverse Fourier transform. So prima facie, it looks like we are going to need n to the q samples. The amazing thing observed by Annie Coit and her collaborators recently was that polynomial times q times n is enough. But they used elaborate Prony-based methods, and they had to solve eigenvalue problems and solutions of a large system of equations and such. And so everything broke down below the noise levels of 20 to 40 dB. So together with my pupils, we decided to do such a thing. We solve a series of univariate problems as Annie proposed, but we use my easier method, and then it turns out that it's robust under noise. So okay. So here is the data we took is data from her paper having 1000 point sources in 3 dimensions. We took so many samples. The algorithm ran pretty fast, I think. Then remember that their results stopped at 30 to 40 dB. We can go all the way to -10 dB and still recuperate a significant amount of number of points with a small margin. At 20 dB, we can recuperate almost everybody with a, again, very small margin.
Here, you're assuming that you know the number of sources?
No, we don't know the number of sources. That's the reason why we want to find out how many we have recovered correctly.
But you're saying that you're retrieving the signals. I thought your objective was to retrieve the signals noise free in some sense. No.
No, it was not noise free. It was -10 dB noise.
I understand, but you wanted to extract the signals from the noise.
Yeah.
But you did not know how many of them there were to begin with.
That's right, but we can find it. That's what this table is showing. We could recuperate 903 of those points. So we cannot find all 1000 points, that we don't know. But we could recuperate 903 points. So my algorithm will probably report that there were so many points which are recuperated correctly.
Yeah, that's pretty interesting, because typically, particularly for those sources that are very closely
Mhm.
that are closely spaced,
Yeah.
typically, if you're not specifically hunting for that number, typically you will recover only one of them as a combination of the two.
So we tried this music and split algorithms also, and
Right.
just for 12 points, and they failed even at 60 dB to detect all of them. But our algorithm can do this at 90 dB, all of them.
Mm-hmm.
Okay, so I was able to extend these localized kernels for in many different settings for Jacobi polynomials, of course, then for spherical polynomials, which will be important for the rest of my talk. I can do this also for Laplacian eigensystem and manifolds, harmonic polynomials, and a generalization which I have called data spaces. So coming to classification then, because we are on the topic of super resolution problems, again, the question is the class boundaries might overlap. And then we are getting samples from a convex combination of these two measures. The problem is to figure out what is the support of mu1 and what is the support of mu2. I did some work with Alex Cloninger using Hermite polynomials. And then I asked my student Ryan Woodhout to do this on the sphere. So once more, the localized kernel is defined in the same way. Here is my definition for the unit sphere. This is the distance. For this problem, I decided to use Chebyshev polynomials because we can compute them very easily using non-uniform discrete cosine transform. And they satisfy, of course, the same sort of nice localization property. So first, let's say that we have just one class. So I want to detect where is this data located. I need, of course, some assumptions to prove anything. And one of the assumptions is that the data should not be too sparse. So around every point in the support of this measure, it should behave at least like R to the alpha for some alpha. So here is the algorithm. I look at the sum of the squares here and compare it with the maximum over the data and set some threshold, which is a hyperparameter of my problem. Then this set is approximately the same as the support of the major mu star up to depending upon what the threshold is, that divided by n. So we can detect this fairly accurately in theory. Okay, but this is only for one measure. We have a combination of different measures. So I'm going to say that it has a fine structure, which means that there is a partition of the support of the major mu star. And then I have to account for the fact that the supports can touch each other. So at some point, I have to draw a little ball around it and say that this is uncertain region. I'm going to assume that change my minimal separation requirement, then the measure of that exceptional set is going to be 0. So in this presentation, I'm going to assume that the boundaries are disjoint and separated by the distance eta. Okay. I don't formulate the measure mu k explicitly. The mu k is just going to be the restriction of mu star to this support. My goal is to find these supports. So once more, remember this set g theta. This g theta will have exactly so many, a partition consisting of so many elements which are separated by the distance half the minimal separation, and each of those clusters will approximate the support of the measure mu sub k, which is the support of the class k. Okay, that looks too good to be true, so I needed a reality check. In my paper with Alex, he tried a hyperspectral imaging data set and it worked very, very well, better than any existing technology. Ryan is still working to do this on the sphere. But here is a diagram. So these are the actual supports, and our sets G, these components G of G theta will be something like this. And here is the reality check. So we took the 2 moon data set, and then he could detect the supports of the measure perfectly without knowing any of the labels here. So then afterwards he checked just one label here and one label here, and that just extends that label to the whole cluster here. Then it gives him 100% classification just with 2 labels here. If you notice, there was a fine squared here. So he tried it without the square. It gives theoretically, it gives a better approximation to the measure itself. But it's an oscillatory kernel, so it doesn't approximate the supports very well. So one needs the square here. I'm still hoping that somebody will help me to get a better, a more interesting example of this. So this is just the beginning. Okay, then I come to the last topic. As I mentioned, I want to do a direct function approximation without trying to minimize a loss functional so crudely. I have already demonstrated to you that I can do this in the trigonometric setting. So what is the problem? The problem is that we are just given some data in practice. We don't know where it is. So all the approximation theory results have to do with cube, sphere, torus, things like that. But the data doesn't become dense there. So uh, I was fond of proving such theorems, and I proved quite a few of them. But now I think this was all useless because the data doesn't live there. Then we cannot choose the data points judiciously. Okay, that problem we had solved again on the cube and sphere and so on. But in classical approximation theory, we need to choose these x sub j's. And the existence theorem just say that, okay, there exists some x sub j's, but God knows how to find them. But then I think it is useless because we are given the data, we don't get to find it. And then, of course, there is a noise. So there was a lot to think about, and it took about 30 years or so to think about it, but eventually I think I'm getting there. So one of the things which I learned in the meantime was the manifold assumption. So we don't know where the data is, but we can imagine that it is sampled from a nice, compact, smooth, and whatever nice adjectives you can think of, that kind of manifold. The only caveat is that the manifold is not known. And then we can imagine that this manifold is so rigged that the data is sampled from the volume measure of this manifold. Okay, of course, the data doesn't given to you lies in a high dimensional ambient space. But we just imagine that the submanifold is a small dimensional manifold. So the main question is then, where is this manifold? What can we say about that? And the other question is then, after we find this out, how to do function approximation. So here is the general approach. One approach here is to construct what is called a graph Laplacian. And then Belkin and Yogi and Amit Singer and many people have shown that this graph Laplacian itself approximates the manifold Laplacian, the eigendecomposition approximates the eigendecomposition of this thing. And then because this is my 15 minutes of glory, then I just want to advertise that I've done so much work on constructing approximation using this eigendecomposition directly or indirectly via such a kernel. Then I presented this very proudly to Lorenzo Rosasco, and he said that is useless because we don't know what this manifold is, and if we try to do so many approximations, then the entire approximation theory paradigm will break down. So, okay, so I did some work in this direction together with Alex Cloninger, again based on harmonic polynomials, and it worked pretty well. So I asked my student to put it on the sphere again. So here is the unknown manifold. We can project it to the sphere like this. So we get there is no loss of generality in assuming that this is a submanifold of the sphere. By putting it on the sphere, I get advantage of having a nice one variable orthogonal polynomial system on the sphere, and then it is a compact set to begin with. So here is my localized kernel as usual. It's the same filter which I had shown you earlier. But now instead of using it with exponentials, I use it with the correct ultraspherical polynomials corresponding to the sphere of lower dimension, the ambient manifold dimension. So I'm looking at these orthogonal polynomials, and then I showed in 2004 that these kernels are properly localized, as I showed you earlier. So here is the theorem. We are given the data xj, yj. We use this kernel, and here is my approximation. That's it. There is no optimization, no nothing like that, no assumption on the data either. So if the data doesn't come from a function, then this will show up, because our theorem will say that if it comes from a nice function, this will converge to the right function at the right rate. So in mathematics, this is a nice thing. If the experiment doesn't agree with the theory, then we say that the experiment is wrong. It's not like in sciences. So anyway, here is my approximation, and I will show that it gives you the right rate of approximation if the manifold and some other technical conditions are satisfied. Okay, when I show this expression to people, then people are reminded of an Nadaraya-Watson estimator. And then I guess I should make some comments before I go further. Then, so I'm not the first one to try this. But in the Nadaraya-Watson kernel, they have a fixed kernel. But I'm looking at a sequence of kernels depending upon this n. Then Nadaraya-Watson kernel is working on Euclidean spaces. My kernel will work on unknown manifolds. Nadaraya-Watson kernel works with a scaling factor. So this is what we call in approximation theory a spline paradigm. So it is working by shrinking the support of that kernel. This is working with the degree converging to infinity. So it's what we call a polynomial paradigm. The Nadaraya-Watson kernel localizes in Euclidean space with changing h. So as I mentioned, it is shrinking the domain. I'm working on unknown manifolds. So my localization is adaptive. It is actually like an adaptive nearest neighbor method, but all the neighbors are considered and given different weights. The Nadaraya-Watson kernel requires a positive kernel. I don't want a positive kernel here for approximation, and there is no saturation, so there is no limit to how smooth functions you can approximate in theory. In my theorem, there will be some problem, but that's just an artifact of our proof.
Shrinking. When you mean a shrinking kernel, here is.
I mean,
but is this are we still operating in the spectral space or in the
Nadaraya-Watson kernel operates on the Euclidean space, and then as you know, the way it works is it becomes more and more localized as the scaling changes. So effectively, it is doing approximation on a shrinking domain. I'm not doing that. I'm doing approximation on a whole unknown manifold. And effectively then, because of my localization, this kernel is making an adaptive localization on the whole manifold. Okay, here is the theorem. It's kind of complicated to state, but here is the standard paradigm that I have a certain noisy signal, and then I'm going to look at the expected value of that signal. And then, if my M is the right way, M and N are related in the right way, then with the tau probability, I have this estimate like n to the gamma. And because of the way we prove it, then because of the curvature of the manifold, basically, I have to have this gamma less than 2. We are working on how to improve this. So it does two things in one stroke. If I use this with f equal to 1, then it gives me a density estimator. Normally, if you are doing probability density estimation, then we use positive kernels. But in approximation theory, positive kernels are known not to give good approximations. So here I'm using non-positive kernels. And if we insist on having something positive, we just put an absolute value around this f sub n. And then we get a much better approximation to the density. As I said, if we are interested in function approximation, then it is customary to assume that the measure itself is the volume measure of x. So this f sub 0 is 1. And then I get a result on function approximation. Again, the kernel was universal kernel. I made absolutely no assumptions on the data there. These theorems are then proving that if you have a nice function, it will actually give you an approximation at the right rate of approximation. This is the best possible known in approximation theory. So my kernel was a universal kernel. I made no assumptions there, as I just said. Then the degree of approximation depends only on the manifold dimension. So here is the connection between m and n. So if you choose the smallest m, then you will get the same rate which everybody is familiar with, log m over m to the gamma over plus 2 gamma. But this q is the dimension of the ambient actual manifold, not the ambient dimension. Even if I am assuming that my manifold is an unknown submanifold of a high dimensional sphere, the dimension of the sphere probably plays some role in this constant, but not in the rate of approximation. Then I don't need to learn the manifold first. So this question which Lorenzo Rodasco raised is now completely solved. I don't have to go through a series of approximations via eigendecomposition or finding some sort of atlas or something like that. Here is a very direct method. And then, okay, it's fashionable to work with deep networks and recurrent networks and so on. And so if it is important for the purposes of getting grants and such, we could implement this using either a deep or recurrent network because we are working with orthogonal polynomials. The expansions in orthogonal polynomials can be implemented by a recursive algorithm. If we unfold it, then we get a deep network. If we don't unfold it, then we get a recurrent network. But the important point is we don't need any training for these deep networks. As everybody knows, deep networks take a humongous amount of data to train, and then the training itself is very slow. So these problems are solved in my in theory in my method. So again, I need a reality check here. Everything looks strange. So there is a doctor at National Institute of Aging, and he proposed to me this problem. They are interested in a problem similar to signal separation, except that please remember I'm a mathematician. J represents to me just an index. There is no square root of -1, which is I here. There is no I here as in signal separation. And I still want to do the same problem. Okay, in this case, I do know that the coefficients are like this, and there are only two components here. So we are dealing with a two-dimensional manifold. We chose for our training data and test data, the lambda1 and lambda2 in this way. We took the training data without noise because we already know the model. But for the test data, we don't have that luxury. So we took 128 points with this this noise, which according to MATLAB gave us a SNR of about 73. Oh, I'm sorry, this capital N refers to the degree of the polynomial, which I used, nothing to do with this N. And the error was measured by the percentage error. And we got results which are accurate up to 68% for, sorry, 0.68% for lambda1 and 0.54% for the next one. So it's maybe we can improve upon this. This requires further work, but at least it doesn't look like it was all junk. So thank you. Thank you very much.
I guess there is a virtual way. There is a modern way of clapping. What was it again here? Yeah, there you go.
Okay. Oh, I
This,
see. Okay, thank you. I'm
yeah, this is
familiar
the
with that.
modern way. This is the modern way of clapping. Yeah.
Thank you.
Thank you. That was very enlightening. The one question I have is particularly towards the end there, when you're talking about this being able uh, to basically do your representation without any training.
Yeah,
I think I asked you when we talked actually together. I asked you the question pertaining to the fact that the I guess neural networks the at least the value that people sort of associate with them is this ability to have this universal universal representation for many classes, right? And then
it's the same.
subsequently use in some sense that representation to actually guide the classification, right?
Yeah. Okay,
Uh,
this is not for classification. For classification, I showed you that we have to use, I'm proposing that we use something similar to signal separation. This is for regression problems.
this is just regression. So okay, that's basically what my my confusion came about, because I couldn't see I couldn't see the link to
Uh-huh.
the inference or classification problem.
Now, for classification, as I proposed this other method where you look at such a kernel and then you find out where it is large. So like this. And this set will then split into exactly as many clusters as there are classes. And then you just pick the labels, one label per class cluster.
Right, right.
That's like the beam forming and analog of beam forming in signal separation.
And the other question that I had, you may have mentioned it, but maybe I missed it. In terms
Mhm.
of the how hard is it to compute these things?
It's extremely easy. It's very easy. You have recurrence relations to compute orthogonal polynomials, and there is a algorithm called Clenshaw algorithm to compute this kind of kernels.
It's
So
called what? What kind of algorithm?
it's called Clenshaw algorithm. How can I do this? I will put it in the chat. No, yeah, chat. Clenshaw algorithm.
Lenshaw. Okay, I'm not familiar actually. Okay.
But there are also some
This is the proper
faster.
name. This is a proper
Yeah,
name, right?
yeah, it's a proper name.
Yeah.
And there are also fast algorithms which Daniel Potts has developed. I will type his name also. On his website, you will find some code to compute these things very fast.
Yeah, I'm not familiar with that actually. Okay. That's good.
This I know that it can be done fast because many people have tried this to compute these kernels.
Okay. Are there any questions from other people, the audience?
Can
Right.
I can I ask a quick question?
Yeah,
So in the middle of the talk, you mentioned somewhere in a multivariate approximation to some polynomials or functions where there's more than one argument. in the function.
No,
In the
no, not
multivariate case.
it's all multivariate, but I think you're probably referring to this problem. Are you referring to this?
Yes, somewhere here.
It is not function approximation. This is signal separation, where I'm trying to separate the signals at WK.
Oh, I see. Okay, I see. So I was maybe X is the single variate of the function you're interested. Okay. I was going to ask something about approximating multivariate functions, but maybe
Okay, I talked about 3 different topics. One was signal separation, one was classification, and one was approximation problem. The
got it.
approximation and classification were necessarily multivariate,
Yeah.
and this was something which is for multivariate signal separation also. So
Okay.
everything was about multivariate functions. I wonder what part your question is about.
Yeah, so on the multivariate approximation, I was curious, like is there any theory if the two variate or multivariate does not commute? So usually we think about, coordinate space where x and y are just the scalar functions, right? So x, y, just the commute. So are there any sort of, how much is known if, let's say, the two variate or the multivariate of a function does not commute? And how would I think about, are there any sort of established result there? So the reason I'm asking is because in sort of,
Maybe I can stop and you can write on the whiteboard or something, because I'm having difficulty understanding what it means by commuting.
sure, okay, great. So let's say I have a function f as a argument. Maybe I have p and q, where p and q are two variates of this function. And by commuting, I mean the commutator. So if I have p times q minus q times p is equal to 0. So I'm calling this as a commuting case. So there's
the Lie bracket, they call
the
it.
Lie bracket.
Yeah, the physicists call it the Lie bracket.
Yeah, exactly. So if this is not equal to 0, so I'm calling this a non-commuting case. And so I was really interested in the scenario where if I have a function of two arguments where the two argument actually does not commute, and how can I sort of thinking about,
These two arguments are not Euclidean arguments, they are vector fields then. Is that so?
arguments about?
If these are real numbers, then of course they will commit. But if they are vector fields, then they will not commit. Then what you are calling?
Yes, exactly. So if I have
Yeah,
yeah.
I have not looked at approximation of functions on vector fields.
Okay, I see. Yeah, I'm just curious because a lot of the approximation theory here works also for quantum mechanics. So there is a lot of operators and quantities that does not commute. That's like the intrinsic property of quantum mechanics. And I study quantum algorithms, so I was curious, like if there is anything. I see a lot of connections here in a univariate case, and I'm curious, like if there is anything on a bivariate or multivariate case where the two variable does not commute.
Now, multivariate Euclidean case, I have not worked on functions on vector fields. So if you can send papers on this to read, then we can talk further on this.
Okay, I see. Yep. Thanks a lot for the explanation. Very nice talk.
Thank you.
Any other
I
question?
have also one question. So Dr. Mhaskar, I mean, I wouldn't claim that I understand all the theory you presented here. Am I audible properly?
That it was trivial. So I'm glad that you did part of it. Okay.
Yeah, but I have some questions regarding, manifold learning, or also like you presented the classification example for the moon data set. So what I understood was that you're trying to learn the support of the different classes basically. And once you have learned that, according to that, you will classify any test data point.
Yeah.
I'm not sure if you are aware of adversarial learning or adversarial examples. So that's
Yeah.
what I wanted to ask actually. So
Yeah.
what if have you tried your theory in this paradigm of adversarial examples, or if your manifold has some kind of holes? So in that case, does it affect approximating these functions in any way?
I just proved these theorems a couple of years ago, and I don't have uh, such support of people who can actually try this in different applications. So I can prove some theorems and do some Mickey Mouse experiments like what I showed you. And if I find somebody like Alex Cloninger who can try this in a more serious setting, then I'm lucky about it. So again, I will be very happy to work. I'm looking for somebody to try this and give me some further reality check and further problems to work on also. But I have so far only proved some theoretical stuff here.
Okay, thank you. But I'll go through your papers. I mean, it was quite interesting stuff which you presented. Thank you.
Thank you. I'd love to talk with you further also.
All right. Any more questions? Okay. If there are no questions, thank you again. And
Thank you. I have a question for you, Dr. Quinn.
yes.
Amit. So I showed this multivariate signal separation, and I read in the papers that this has something to do with ISR imaging. But I asked the author, and she was only a mathematician. She didn't know how it comes up in engineering. So can you send me some references where these kind of problems appear in engineering?
I actually do have some old papers on ISAR
Okay,
where
that will be good. I think if it tells me how this problem will come up in either ISAR or tomography or whatever, but some engineering thing to relate it to.
right. And what we were trying to do there was actually to it's in some sense it's kind of the generalization of the Kullback-Leibler distance, where you have actually more than one density. If you have a multiple density problem, and you're trying to measure, in some sense, the separation among the densities, and we applied it. We use this thing called Jensen-Renyi divergence that we developed for multiple distributions, and then we applied it as we always do in engineering. We have to find. You come up with a hammer, you have to find the nail, and the nail was ISAR.
I see.
Yeah.
So do you mind sending me some paper about this, which I
Sure.
could understand?
Yeah, I have to remember, first of all, that paper is like 20 years old or something. So I have to find it, and I have to remember. I think I remember who the authors were. I think it's
yeah, that is fine.
yeah,
Whatever.
but Ben and some other student. Yeah.
All right.
All right.
So
Thank you very much. We'll be in touch. Okay.
Yeah.
Thank you
Bye-bye.
again.
Have a nice day.
You too. Bye bye. Thank you, everyone. Thank you. Bye bye.